CinePile, a long video question answering dataset and benchmark abstract. Current datasets for long-form video understanding often fall short of providing genuine long-form comprehension challenges, as many tasks derived from these datasets can be successfully tackled by analyzing just one or a few random frames from a video. To address this issue, we present a novel dataset and benchmark, CinePile, specifically designed for authentic long-form video understanding. This paper details our innovative approach for creating a question-answer dataset, utilizing advanced LLMs with human-in-the-loop and building upon human-generated raw data. Our comprehensive dataset comprises 305,000 multiple-choice questions covering various visual and multimodal aspects, including temporal comprehension, understanding human-object interactions, and reasoning about events or actions within a scene. Additionally, we evaluate recent video-centric LLMs, both open source and proprietary, on the test split of our dataset. The findings reveal that even state-of-the-art video-centric LLMs significantly lag behind human performance in these tasks, highlighting the complexity and challenge inherent in video understanding. 1. Introduction. Large multimodal models offer the potential to analyze and understand long, complex videos. However, training and evaluating models on video data offers difficult challenges. Most videos contain dialogue and pixel data, and complete scene understanding requires both. Furthermore, most existing vision language models are pre-trained primarily on still frames, while understanding long videos requires the ability to identify interactions and plot progressions in the temporal dimension. In this paper, we introduce CinePile, a large-scale dataset consisting of approximately 305,000 question-answer pairs from 9,396 videos, split into train and test sets. Our dataset emphasizes question diversity, and topics span temporal understanding, perceptual analysis, complex reasoning, and more. It also emphasizes question difficulty, with humans exceeding the best commercial vision or omniscient models by approximately 26%, and exceeding open-source video understanding models by 70%. We present a scene and a few question-answer pairs from our dataset in Figure 1. Consider the first question. How does Gru's emotional state transition throughout the scene? For a model to answer this correctly, it needs to understand both the visual and temporal aspects, and even reason about the plot progression of the scene. To answer the second question, what are the objects poking out of the book cover, and what is their purpose? The model must localize an object in time and space and use its world knowledge to reason about their purpose. CinePile addresses several weaknesses of existing video understanding datasets. First, the large size of CinePile enables it to serve as both an instruction tuning dataset and an evaluation benchmark. We believe the ability to do instruction tuning for video at a large scale can bridge the gap between the open source and commercial video understanding models. Also, the question diversity in CinePile makes it a more comprehensive measure of model performance than existing benchmarks. Unlike existing metrics, CinePile does not overemphasize on purely visual questions, such as what color is the car, or on classification questions, for example, what genre is the video, that do not require temporal understanding. Rather, CinePile is comprehensive with diverse questions about vision, temporal, and narrative reasoning, with a breakdown of question types to help developers identify blind spots in their models. The large size of CinePile is made possible by our novel pipeline for automated question generation and verification using large language models. Our method leverages large existing sets of audio descriptions that have been created to assist the vision impaired. We transcribe these audio descriptions and align them with publicly available movie video clips from YouTube. Using this detailed human description of scenes, powerful large language models are able to create complex and difficult questions about the whole video without using any explicit video input. At test time, video-centric models must answer these questions from only the dialogue and raw video, and will not have access to the handwritten descriptions used to build the questions. Dataset and artifacts are available at this link. 2. Creating a long video understanding benchmark. Our dataset curation process has 4 primary components. 1. Collection of raw video and related data. 2. Generation of question templates. 3. automated construction of the question-answer dataset using video and templates, and 4, application of a filtering pipeline to remove malformed questions. 2.1. Data collection and consolidation. We obtain clips from English-language films from the YouTube channel Movie Clips. This channel hosts self-contained clips, each encapsulating a major plot point, facilitating the creation of a dataset focused on understanding and reasoning. Next, we collected audio descriptions from AudioVault. Lastly, we collect movie information for each scene, such as genre, actors, and main plot from IMDb. Figure 2. Question Template Generation Pipeline. We begin by substituting the first names in human-written source questions and then cluster them. We then feed a selection of questions from each cluster into GPT-4, which in turn outputs question templates which are used in the next stage of dataset creation. See Section 2.2 for more details. Getting visual descriptions of video for free? Audio descriptions, or ADs, are audio tracks for movies that feature a narrator who explains the visual elements crucial to the story during pauses in dialogue. They have been created for many movies to assist the vision impaired. The key distinction between conventional video caption datasets and ADs lies in the contextual nature of the latter. In ADs, humans emphasize the important visual elements in their narrations, unlike other video caption datasets, which tend to be overly descriptive. We use the audio descriptions as a proxy for visual annotation in the videos for our dataset creation. Scene localization in AD. The video clips we have gathered are typically 2 to 3 minutes long, while audio descriptions, or ADs, cover entire movies. To align descriptions with video, we transcribe the audio from both the movie clip and the whole movie AD file using an automatic speech recognition system, Whisper, an enhanced version of Whisper designed to offer inference and more precise word-level timestamps. We then embed the first 3 and last 3 lines of the text transcription of a YouTube movie clip using a sentence embedding model, where fast text is used. We similarly embed all the sentences in the corresponding movie AD file. We then localize the YouTube clip within the AD file via the rolling window algorithm. We then extract the AD data that lies between the matched start and end of the movie clip embeddings. This localized text contains both the visual elements and the dialogue for the given YouTube clip. This serves as a base text for creating the QA dataset, which we will discuss in the rest of the paper. For the rest of the paper, we will refer to the human-written description of the scene as visual description, and the speaking or dialogue part of the video as dialogue. When combined, we will refer to both data sources as scene text annotation. Sentence classification. When we transcribe an AD file, the text contains a human's visual descriptions and the movie's dialogue. However, the transcription model does not label whether a given sentence belongs to a visual description or a dialogue. Since we plan to create a few questions solely on the visual components of the video, the distinction is important to us. To categorize each sentence as either visual or dialogue, we fine-tuned a BERT base model using annotations from the MAD dataset, which contain labels indicating whether a sentence is dialogue or a visual description. We applied a binary classification head for this task. For training the classification model, we split the MAD dataset annotations into an 80-20 training evaluation split. The model achieves 96% accuracy on eval split after 3 epoch training. Qualitatively, we observed that the model accurately classifies sentences in the data we curated, distinguishing effectively between dialogue and visual description content. 2.2. Automated question templates. Many prominent video question-answering benchmarks were written by human annotators. The question-answer pairs are typically curated in one of 2 ways. 1. Human annotators are given complete freedom to ask questions about a given scene. They are asked to focus on specific aspects and are trained or provided with examples of questions, encouraging them to write more questions in a similar style. For instance, in the perception test benchmark, annotators are directed to concentrate on temporal or spatial aspects, while for the next QA dataset, annotators mainly focused on temporal and causal action reasoning. Questions. Figure 3. Extracting templates from human-generated questions. We share 10 samples from each question cluster and prompt an LLM to create a few templates and a prototypical question. See Figure 2 and Section 2.2 for more details. During early experimentation, we found that providing a range of templates, along with scene text annotation to an LLM, helped it create more detailed, diverse, and well-formed questions. So we decided to use a template-based approach for question generation. Rather than confining questions to a few hand-curated themes, we propose a pipeline to create question templates naturally on top of human-generated questions. The automated question template generation pipeline is illustrated in Figure 2. Our starting point is approximately 30,000 human-curated questions from the movie QA, TV QA, and perception test datasets. We cluster these questions, select a few representatives per cluster, and then use GPT-4 to discern the underlying themes and write a prompt. First, we pre-process the questions by replacing first names and entities with pronouns, as BERT models embeddings over-index on proper nouns. Hence, the resultant clusters end up with shared names rather than themes. For instance, "Why is Rachel hiding in the bedroom?" is altered to "Why is she hiding in the bedroom?" We used GPT 3.5 to do this replacement, as it handled noun replacement better than many open-source and commercial alternatives. The modified questions are then embedded using Whereas LabSE or UAE Large V1, a semantic textual similarity model which is a top performer on the MTEB leaderboard. When the first names were replaced, we observed significant repetition among questions, which prompted us to duplicate them, ultimately resulting in 17,059 unique questions. We then perform k-means clustering to categorize the questions into distinct clusters. We experimented with different values of k equals 10, 50, 100. Qualitatively, we found k equals 50 to be an optimal number of clusters, where the clusters are diverse, and at the same time clusters are not too specific. For example, we see a high school dance, specific question cluster when k equals 100, and these questions are merged into an event cluster when we reduce the number of clusters to 50. The perception test questions are less diverse, as human annotators were restricted to creating questions based on a small number of themes, so we used k equals 20 for this set. The number of questions in each cluster varied, with counts ranging from 60 to 450. We selected 10 random questions from each and used them to prompt GPT-4 to create relevant question templates, as illustrated in Figure 3. We also ablated the scenario of taking the closest 10 questions to the cluster center. We, however, qualitatively observed that random questions produced more general, higher-quality templates. We generate 4 templates for each question cluster, resulting in around 300 templates across 3 datasets. We then manually reviewed all 300 templates, eliminating those that were overly specific and merging similar ones. Overly specific templates and their proto-questions looked like pre-wedding dilemmas, what complicates character Z's plans to propose marriage to their partner, and crime and consequence, what is the consequence of the character's criminal actions. Figure 4. Automated QA generation and filtering. Our process begins with a set of automated templates and scenes. Initially, we filter out the templates relevant to each scene. Next, we pass these templates along with the annotated scene text to GPT-4, which is then used to create multiple-choice questions or MCQs. The generated MCQs are then subjected to numerous filters to curate the final dataset. For more detailed information, refer to Section 2.3 and Section 2.4. The authors also added a few templates that are complementary to the auto-generated ones. This process resulted in 86 unique templates. Following that, we manually binned these into 4 high-level categories: character and relationship dynamics, narrative and plot analysis, thematic exploration and setting, and technical analysis. For a detailed discussion on each of these question template categories, please refer to the appendix. We present 2 sample question templates per category and their prototypical questions in Table 1. Table 1, sample templates and prototypical questions from each of the categories. 2.3, automated QA generation with LLMs. The pipeline for generating questions is shown in Figure 4. While the question templates are general, they might not be relevant to all movie clips. Hence, for a given scene, we choose a few relevant question templates. To do this, we provide Gemini with the scene text annotation of the scene, and ask the model to shortlist the 20 most relevant templates to that scene, out of which we randomly select 5 to 6 templates. We then provide a commercial language model with 1, the scene text annotation, which includes both visual descriptions and dialogue, 2, the selected question template names, for example, physical possession, 3, the prototypical questions for the templates, e.g., what is character name holding, and 4, a system prompt asking it to write questions about the scene. Through rigorous experimentation, we devised a system prompt that makes the model attentive to the entire scene and is capable of generating deeper, longer-term questions as opposed to mere surface-level perceptual queries. We observed that providing the prototypical example prevents GPT-4 from hallucination and also leads to more plausible multiple-choice question, or MCQ, distractors. We also found that asking the model to provide rationale for its answer enhances the quality of the questions. Additionally, we found that including timestamps for dialogues and visual descriptions augments the quality of generated temporal questions. Through this method, we were able to generate approximately 32 questions for each video in the dataset. After experimenting with this pipeline, we analyzed the generated QA pairs and noticed a consistent trend. Most questions are focused on reasoning or understanding. For diversity, we also wanted to include purely perceptual questions. To achieve this, we introduced additional handcrafted prompt templates for perceptual questions and also templates for temporal questions. While GPT-4 performs well across all question templates, we found that Gemini excels particularly with perceptual templates. Therefore, we utilized Gemini to generate a segment of perceptual questions in the dataset, while using GPT-4 for reasoning templates. Our experiments with open-source models indicated superior question quality despite extensive prompt tuning. We present example questions generated by GPT-4 and Gemini, along with their templates, in the appendix. A small proportion of questions produced by this pipeline can be answered without referring to the clip, such as, "What's the color of the blonde woman's hair?" We implemented a few checks to eliminate such trivial or poorly framed questions. We discussed these checks and a few axes of evaluating the question-answering dataset in the following section. Testing the quality of the dataset. While the process above consistently produces well-formed and answerable questions, we observed that some questions are either trivial, with answers embedded within the question itself, or pertaining to abstract concepts that do not require viewing the clip. To prune these, we evaluated our dataset with the help of a few large language models on the following axes, and we either removed the questions from the dataset or computed a metric that the users can use in the downstream tasks. Degeneracy. A question is considered degenerate if the answer is implicit in the question itself. For example, what is the color of the pink house? In our dataset, these types of questions constitute only a small fraction. Manually reviewing all questions being impractical, we employed 3 distinct language models to automate this process: Gemini, GPT 3.5, and Phi 1.5. We presented only the questions and choices to these models, omitting any context, and calculated the accuracy of each question across the multiple models. If all models correctly answer a question, it is likely to be degenerate. We excluded degenerate questions from the evaluation split of our dataset, but retained them in the training set. Vision reliance. When generating the multiple choice questions, or MCQs, we considered the entire scene without differentiating between visual text and dialogue. Consequently, some questions in the dataset might be answerable solely based on dialogue without the necessity of the video component. For this analysis, we utilized the Gemini model. The model was provided with only the dialogue, excluding any visual descriptions, to assess its performance. If the model correctly answers a question, it is assigned a score of 0 for the visual dependence metric. If it fails, the score is set at 1. In later sections, we present the distribution of the visual dependence scores across different MCQ categories. Hardness. We developed a metric to gauge the difficulty of questions for the models, even when provided with full context. For this purpose, we selected the Gemini model, given its status as one of the larger and more capable models. This metric differs from accuracy. For accuracy computation, the models are only supplied with videos and dialogue information, excluding visual descriptions. However, in calculating the hardness metric, we include visual descriptions as part of the context given to the model. In addition to this, authors regularly verified the quality of questions across multiple scenes and fixed any systemic errors that arise in the pipeline. Next, we discuss a human study we conducted on our dataset and some of the findings. Figure 5. Sample failure cases from human study. We conducted a human study to check the quality of questions, and we found a few systemic issues. We fixed all systemic issues in the final version of the dataset. The movie clip for Q1 can be found here, for Q2 here, for Q3 here, and for Q4 here. Table 2. We compare our dataset CinePile against the pre-existing video QA datasets. Our dataset is both large and diverse. Multimodal refers to whether both the video and audio data is used for question creation and answering. For understanding different QA types, refer to section 2.3.3. Human study. Once we finalized the pipeline and generated a reasonable number of questions, we conducted a small human study to help us find weaknesses or systematic problems with the dataset. Each participant, graduate student volunteers, answered 10 questions about 2 different randomly chosen videos. We randomly sampled the 10 questions from the list of all the questions we generated for the scene. We had 25 participants, excluding authors. We also interviewed each participant after the survey to ask if they found any systematic issues in any of the questions they were asked to answer about the video. Later, a panel of authors audited all questions where humans got the answer wrong. We noticed that most of the time when a human got a question wrong, it was likely due to one of the following reasons. I, due to their inability to attend over the entire clip at once. 2, due to their inability to understand the dialogue or understand cultural references. Carelessness in answering, as the correct answer was indeed present in the video. We did notice some problematic patterns with a small subset of questions. The main issue is distractor similarity, where humans found 2 plausible answers, and they chose one randomly. We present a few such examples in Figure 5. We removed the questions from the test set for which we found ambiguous answers. We again conducted a second human study on the test set's final version, and the human accuracy is 73%. The authors have independently taken the survey, and the corresponding accuracy is 86%. Once again, a careful investigation by a team of authors indicates that even most of these wrong answers are due to human error and confusion over the many events in a scene. We conclude from this study that many of the questions are answerable but difficult. We present the question category-level performance in Section 5. 4. A look at the dataset. In the initial phase of our dataset collection, we collected approximately 15,000 movie clips from channels like Movie Clips on YouTube. We filtered out clips that did not have corresponding recordings from end segments. Figure 6. Test split statistics. Left, question category composition in the dataset. Middle, percentage of vision-reliant questions across categories. Right, percentage of hard questions per question category type. Temp, temporal. CRD, character and relationship dynamics. NPA, narrative and plot analysis. STA, setting and technical analysis. TH, thematic exploration. The colors correspond to the same categories across the plots. Refer to the appendix for corresponding plots of train split. Audio-visual, as our question generation methodology relies on the integration of visual and auditory cues, interleaved dialogues, and descriptive audio to construct meaningful questions. We also excluded clips with low alignment scores when comparing the YouTube clips transcription with the localized scenes transcription in the Audio Descriptio AD file, as discussed in Section 2.1. This process resulted in a refined dataset of 9,396 movie clips. The average video length in our dataset is approximately 160 seconds, significantly longer than many other video QA datasets and benchmarks. We split 9,396 videos into train and test splits of 9,248 and 148 videos each. We made sure both the splits and the questions preserved the dataset's diversity in terms of movie genres and release years. We follow the question-answer generation and filtering pipeline, which was thoroughly outlined in Section 2. We ended up with 298,888 training points and 4,940 test set points with around 32 questions per video scene. Each MCQ contains a question, answer, and 4 distractors. As a post hoc step, we randomized the position of the correct answer among the distractors for every question, thus eliminating any positional bias. We filtered out the degenerate questions from the test split. However, we left them in the train set, since those questions are harmless and might even teach smaller models some helpful bias the larger multimodal models like Gemini might inherently possess. Our dataset is large and varied because we used a wide variety of movie clips and different prompting strategies about diverse question types. Each strategy zeroes in on particular aspects of the movie content. We present a scene and example MCQs from different question templates in Figure 1. Please refer to the appendix for other examples. In Figure 6 left, we provide a visual breakdown of the various categories of questions generated in our dataset. A significant portion of the questions falls under character relationship dynamics. This is attributed to the fact that a large number of our automated question templates, which were derived from human-written questions, belong to this category. This is followed by setting and technical analysis questions, which predominantly require visual interpretation. We display the metrics for vision reliance and question hardness, as discussed in Section 2.4. At the category level in Figure 6 middle and right. As anticipated, questions in the setting and technical analysis category exhibit the highest dependency on visual elements, followed by those in the character relationship dynamics and temporal categories. In terms of the hardness metric, the temporal category contains the most challenging questions, with thematic exploration following closely behind. Finally, we compare our dataset with other existing datasets in this field in Table 2, showing its superiority in both the number of questions and the average video length compared to its counterparts. Test split. As mentioned previously, our test split comprises 148 video clips, derived from movies distinct between training and testing to avoid information leakage. Additionally, we have eliminated all degenerate questions from this split, which constituted 4.5% of the generated questions. Following several rounds of manual cleanup and thorough testing, our final count stands at 4,940 questions. Of all the test questions, 33.21% are reliant on visual information. Figure 7. Hard questions according to humans and GPT-4. After conducting the human study, we looked at the questions which human got wrong and the questions which GPT-4 got wrong. Some of these questions are difficult and can only be answered by paying careful attention to the video. The movie clip for question 1 can be found here, for question 2 and question 3 here, and for question 4 here. 5. Model evaluation. In this section, we discuss the evaluations of various closed and open source video LLMs on our dataset, some challenges, and the model performance trends. Given that our dataset is of type multiple choice question answers, MCQs, we evaluate a given model's performance on our benchmark questions by measuring its ability to accurately select the right answer from a set of multiple choice options, containing only one correct answer and 4 distractors. One key challenge in this process is reliably parsing the model's response to extract its chosen answer and mapping it to one of the predefined answer choices. Models' responses may vary in format, including additional narratives, or may only contain the option itself, or have a combination of the option letter and its corresponding text, etc. Such variations necessitate a robust post-processing step to accurately extract and match the model's response to the correct option. Table 3. Model evaluations. We present the accuracy of various video LLMs on the CinePile's test split. We also present human performance for comparison. We also ablate the accuracies across the question categories we discussed earlier. Temporal, CRD, Character and Relationship Dynamics, NPA, Narrative and Plot Analysis, STA, Setting and Technical Analysis, TH, Thematic Exploration. Our evaluation method incorporates a 2-stage process to address these variations. In the first stage, we employ a normalization function to parse the model's response, extracting the option letter, A to E, and the accompanying option text if present. This normalization handles various response formats, such as direct letter responses, for example A, or more verbose forms, for example, answer. D. The Eiffel Tower, ensuring that both the option letter and text are accurately identified if present. Following normalization, the process enters its second stage, which entails comparing the normalized model response with the correct answer key. This comparison involves checking for both the option letter and text in the model response. If both elements are present and match the answer key, a score of 1 is awarded. However, if only the option letter or text appears, the comparison is limited to the relevant part and the score is assigned accordingly. We evaluate various commercial and open-source LLM models, and we present their performance in Table 3. We also present human numbers, author, and non-author for comparison. This distinction is important because the authors carefully watch the video, go back and re-watch the video if necessary while answering the questions. This removes the carelessness errors from the human study. On average, VLM models, both commercial and OSS, are behind human performance on our dataset. While commercial VLMs perform reasonably well, the OSS models perform quite poorly, showing the gap in their capabilities. We present a few QAs which humans got wrong and GPT-4 got wrong and the plausible reason for errors in Fig 7. Among the various commercial VLMs analyzed, GPT-4 T0, GPT-4 Vision, and Gemini 1.5 Pro Video emerge as top performers, each achieving around 60% average performance. Gemini 1.5 Pro particularly outperforms the GPT-4 models in the setting and technical analysis category that is dominated by visually reliant questions focusing on the environmental and surroundings of a movie scene and its impact on the characters. On the contrary, we note that GPT-4 models perform substantially better on other question categories such as narrative and plot analysis that revolve around the core storylines and interaction between the key characters. It's important to note that Gemini 1.5 Pro is designed to handle long multimodal contexts, and while GPT-4 T0 is also a natively multimodal model, GPT-4V only handles 10 frames per video in our evaluation setup. When compared under the same conditions of 10 frames, Gemini Pro Vision, another model in the Gemini series, performs 10% lower compared to GPT-4V. Meanwhile, Claude 3, Opus ranks as the least effective model commercial VLM, trailing Gemini Pro Vision by approximately 5%. Additionally, as discussed in Second 2.4, we provide a hard split in the test set consisting of particularly challenging questions. In Fig 8, we compare the performance of various models on both the average and the hard splits of our dataset. We note that while each model suffers a performance decline of 15 to 20% on the hard split, however, the relative ranking among the models remains unchanged, with the exception of Gemini 1.5 Pro outperforming the GPT-4 models. While a noticeable gap persists between human performance and that of state-of-the-art VLMs, OSS models trail significantly to both. To better understand these trends, we conducted a qualitative analysis of the raw responses generated by the OSS models. This investigation aimed to determine whether the deficiencies observed in OSS models are as significant as presumed, or if there are other factors that might be influencing the overall score. Why are OSS models so far behind? We observed that a key reason for the subpar performance of OSS models is their inability to adhere to the given instructions strictly. For instance, in our evaluation prompts, we explicitly instruct the models to only output the option marker in their responses. However, the OSS models frequently deviated from this instruction, generating excessive and sometimes irrelevant text, including unnecessary personal opinions, rephrasing the answer options, mentioning choices not listed in the provided options, and producing completely unrelated text, such as repeating lines from subtitles or attempting to complete scenes from movies. We present a few examples in Tab 4. We solve some of these issues by implementing a substring matching pipeline within our evaluation pipeline, which searches for the correct answer key within the model's response, only considering those responses that mention a single choice. However, this modification is unable to reliably evaluate scenarios when the model outputs a rephrased version of the text. Hence, we also computed traditional video caption evaluation metrics like BERT score, CEDAR, Rougel, and SPICE for open-source models. We present these results in the appendix and find that the relative ranking between the models remains unchanged. We hope training the OSS models on our training data can help bridge the gap in the performance between OSS models and commercial ones in the future. 6. Related work. 6.1. Video understanding and question answering. LVU 36, despite being one of the early datasets proposed for long video understanding, barely addresses the problem of video understanding, as the main tasks addressed in this dataset are year, genre classification, or predicting the like ratio for the video. A single frame might suffice to answer Figure 8, Models Performance on CinePile Test Split, All Questions versus Hard Questions. Table 4, Analyzing raw responses generated by OSS models, scores assigned by our evaluation pipeline, and corresponding failure modes for the movie clip. Area 51, 2015, Sneaking onto the base scene, 410. A single frame might suffice to answer the questions, and these tasks cannot be considered quite as understanding tasks. Movie QA is one of the first attempts to create a truly understanding QA dataset, where the questions are based on entire plot the movie but not localized to a single scene. On closer examination, very few questions are vision-focused, and most of them can be answered just based on dialogue. Ego schema is one of the recent benchmarks focused on video understanding, which requires processing long enough segments in the video to be able to answer the questions. However, the videos are based on egocentric videos, and hence the questions mostly require perceptual knowledge rather than multimodal reasoning. Another recent benchmark, Perception Test, focuses on core perception skills, such as memory and abstraction, across various reasoning abilities, e.g., descriptive, predictive, etc., for short-form videos. MAD dataset contains dialogue and visual descriptions for full-length movies and is typically used in scene captioning task rather than understanding. Another issue is this dataset does not provide raw visual data. They share only CLS token embeddings, which makes it hard to use. TV QA is QA dataset based on short 1-min clips from famous TV shows. The annotators are instructed to ask what, how, why sort of questions combining 2 or more events in the video. Movie QA manually curates questions across multiple levels, single scene, multiple scenes, full movie, by guiding annotators to develop queries in predefined categories like information processing, temporal perception, etc. TGIF QA is heuristic-based questions, like how many times cat nodded its head, or what happened after event A. It is partially manually annotated with some automation for counting types of questions. Next QA comprises manually curated causal, temporal, and descriptive questions about daily life videos. Long video understanding datasets, such as Epic Kitchens, tend to concentrate heavily on tasks related to the memory of visual representations, rather than on reasoning skills. While these benchmarks are valuable for gauging the extent of visual representation captured by a model, they fall short in providing insights into video understanding. These datasets mainly test a model's ability to recall and recognize visual elements, but do not adequately assess its capability to reason and interpret the context and narrative of videos. CinePile differs from all the above datasets that have much longer videos, and we ask many questions per video to capture the perceptual, temporal, and reasoning aspects of the video. And it is truly multimodal, where the person has to watch the video as well as audio dialogue to answer many questions. Unlike the previous datasets with fixed templates, we automated this process on previously human-generated questions. This let us capture many more question categories compared to previous works. Lastly, our approach to dataset generation is scalable, and hence it is easy for anyone to extend our dataset. 6.2. Synthetic data with human in the loop. Training models on synthetic data is a popular paradigm in recent times. We have seen many advances in generation as well as usage on synthetic data in recent times, both in vision and language. For instance, Self-Instruct proposes a pipeline to create an instruction dataset based on a few instruction examples and categories defined by humans. We mainly derived inspiration and the fact that modern LLMs are quite good at understanding long text and creating question-answer pairs. UltraChat is another synthetic language dataset which is created by using separate LLMs to iteratively generate large-scale multi-turn conversation snippets and provide responses. This allows constructing large-scale multi-turn dialogue data without directly using existing internet data as prompts. Additionally, Eval Instruct automatically generates a diverse corpus of open domain instructions of varying complexities by prompting an LLM and applying iterative evolution operations like in-depth evolving, breadth evolving, and in-breadth evolving. To our knowledge, we are among the first to apply automated template generation and question synthesis techniques to vision and video modalities using LLMs. 7. Discussion and conclusion. In this paper, we introduce CinePile, a unique long video understanding dataset and benchmark, featuring approximately 300,000 questions in the training set and approximately 5,000 in the test split. We detailed a novel method for curating and filtering this dataset, which is both scalable and cost-effective. Additionally, we benchmarked various recent commercial video-centric LLMs and conducted a human study to gauge the achievable performance on this dataset. To our knowledge, CinePile is the only large-scale dataset that focuses on multimodal understanding as opposed to the purely visual reasoning addressed in previous datasets. The dataset is publicly available at the URL. Additionally, we plan to set up a leaderboard for the test set, providing a platform for new video LLMs to assess and benchmark their performance on CinePile. Despite its strengths, there are still a few areas for improvement in our dataset, such as the incorporation of character grounding in time. While we believe our dataset's quality is comparable to, or even better than that of a mechanical Turk annotator, we acknowledge that a motivated human, given sufficient time, can create more challenging questions than those currently generated by an LLM. Our goal is to narrow this gap in future iterations of CinePile. This concludes the reading of CinePile, a long video question-answering dataset and benchmark on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.